Thank you for this kind introduction. First, I would like to acknowledge my co-authors, Eitor Raf Toralson and Jonas Thor Snæbjörnsson from the University of Iceland. I have prepared for 15-minute presentation, but bizarre situation, I will take more questions. So, finite element analysis of the interface between FRP and concrete. So the outline of the presentation, a brief introduction, a literature review. Then I will outline the approach. Outline the approach we are proposing. I'll take some time to present the material models we are using, then to present the finite element model formulation, some numerical results, and concluding remarks. So, as today, test today showed, FRP are widely used and widely recognized technique for strengthening and rehabilitation of concrete structures. They are easy to implement, and furthermore, they are quite effective. So if you have a damaged structural element, if you are using FRP for retrofitting, often, so many times, I won't say every time, but often the element regain its initial characteristics. Furthermore, if you compare a structural element with FRP, externally bonded FRP reinforcement, with an identical element without externally bonded FRP reinforcement, the former has better mechanical characteristics and better performance in terms of ductility. However, as everybody here knows, FRP applications requires a sound knowledge of the adhesive layer behavior. So this is mainly because of the premature failure that can occur due to debonding failure, and that could prevent the full utilization of the theoretical material properties of the FRP components. So some models that have been proposed to simulate the debonding failure, and how to model the debonding failure. So basically, in some cases, we should consider mixed mode conditions. So within the framework of damage mechanics based formulation, which we will not use, but within a damage mechanics based formulation, we can have mode 1 and mode 2 failures. So opening or shear failures. So quite often, we should consider a combination of mode 1 and mode 2. Some cases reported in the literature, which shows when this is needed. So I will focus on the last one. So if you have initially straight structural element with the increasing curvature due to the applied gravitational load, for example, you will have at the interface between concrete and, for example, FRP element bonded on the soffit surface, a mixture between mode 1 and mode 2. So here I am using damage mechanics based formulation to make a difference between the two modes. However, our approach uses damage mechanics to model the concrete failure behavior. So I will not use a fracture mechanics based formulation to model any fracture in concrete. So historically, the initial tries to model the debonding are assuming linear, elastic, and isotropic material response. And the probability of debonding is predicted by defining a limit load level. So some models are listed below. So basically, within these models, the debonding onset is associated with the exceedance of some critical material strength, depending on the model. So the drawbacks of these models are that they do not take into account failure in concrete and concrete failure behavior, concrete strain softening behavior. So mostly common in the reported approaches is the cohesive, to use cohesive finite elements to model the interface. So maybe the first contribution, at least that the one we have found in the literature, Ueda and Dai, they use the cohesive finite elements at the interface between FRP and concrete to model opening failure due to opening stresses or mode 1. And they assumed that damage or degradation in concrete is limited in a thin zone, narrow zone near the interface. So therefore, all debonding possibilities, all options for debonding have been lumped in the cohesive finite elements. So then you can see the further development of the ideas based on the fracture mechanics approach. So reportedly, fracture mechanics based model use traction separation relationship in the cohesive zone to model the nonlinear mechanical behavior of the interface. Furthermore, they already reportedly can capture high stress intensity and account for the fracture properties of concrete, FRP, and adhesive. So general drawback for models which should assume cohesive finite elements is that the crack trajectory should be known in advance. So you should know where to predefine your cohesive elements. This is not the case. Fortunately, in our problem, this is the case. But in general, if this is not the case, if the trajectory of the crack is not known, you should predefine cohesive elements all over your mesh, or assume another strategies. So this could make the model computationally intensive. So in the approach we are proposing, so we are defining material models for all the constituencies, for the FRP material, for the adhesive layer, and for concrete. Then the material models are applied to reproduce experimental setup, which is widely used to model peeling off debonding, which includes mode 1 and mode 2 failures. The scope of our study is limited to normal strength concrete. So this allows us to make the assumption that all failure due to tensile stresses is lumped into the concrete substrate. And thus we can make a simplification to define only debonding within the fracture mechanics based approach, mode 2. So we define only a shear failure. So the approach, all the components of the experimental setup, which will appear in the next slide, are explicitly modeled in terms of geometry, except for the adhesive layer, in 3D setup. Then a numerical algorithm governing the state of the interface nodes, which are initially fully coupled, and then uncoupled in function of the developed shear stress at the interface, is applied in a general purpose finite element, general purpose code for finite element analysis, ANSYS mechanical APDL. The flow chart of the numerical procedure is shown on the right. So basically, we are using incremental procedure to simulate the quasi-static loading for each increment of the applied load. Stress and strain distributions are defined throughout the constituencies based on the stress and strain distributions. Constitutive relations for concrete and for FRP are run. Also, the constitutive relation for the interface with the simplification that failure at the interface or in the adhesive layer can be due only to shear stresses for normal strength concrete. So material models for concrete, instead of using fracture mechanics, we are using smeared crack model, so rooted in continuum damage mechanics. In the stress-strain constitutive relationship for concrete, we are introducing a damage variable. So basically here we have elasticity coupled with damage. So the simplest case is to use isotropic damage variable. So for engineering applications, this yields good results comparing experimental data and numerical data. So damage variable D depends on the set of model parameters which should be experimentally identified, and variable epsilon equivalent, which depends only on the positive components of the strains. So the principal strains, only positive strains provoke cracking, so we are retaining only positive strains. So then we should first match our material constants. So basically, for example, this can be illustrated by the following procedure. For example, you know the grade of the concrete you want to use. You have initial value of the elasticity modulus, and you are tuning the model constant epsilon 0, C, and D to match, for example, the compressive strength of this concrete grade. So here it is not shown, but identification should be completed not only by simulating the compression test, but also some tension test, for example, tension by flexure test. So for the adhesive layer, we are using empirical-based relationship. Here it is illustrated with the simplest possible relationship, bilinear relationship. So reportedly, the nature of the relationship doesn't matter on the overall response. So you can use also nonlinear relationship, but the output is not so affected by the form of the relationship you are using. Again, the assumption we are basing our research on is that the tensile strength of concrete is much less than the strength of the adhesive layer. So again, illustrated the procedure which models debonding. Initially, you have coupled nodes at the interface, one node for the concrete. At each point, one node for the at each point on the interface, 1 point for the concrete, and one node for the FRP. In function of the shear stresses you have at the interface, you have some prescribed displacement, for example, of the FRP nodes with respect to the concrete nodes. And finally, when all the nodes are separated, you don't have any more rigid body, and the analysis stops. FRP material, linear elastic until failure in 3 dimensions, unidirectional FRP should be modeled by defining 5 model constants. So the finite element model, the experimental setup taken from the literature, is shown on the left, and the finite element mesh generated for the numerical experiments are shown on the right. So in the figure on the right, in green are highlighted the initially coincident nodes with fully coupled degrees of freedom. So basically, our explicitly modeled constituencies are meshed with solid finite elements, except for the interface, where a pre-meshing with a not solved finite element is performed to first obtain a more regular mesh, and second to predefine the positions for the initially coincident nodes at the interface. So some numerical results. This is the reproduction of the model setup with angle of inclination of the inclined FRP plates, 30 degrees. So as you can see, the procedure, generally speaking, is mesh dependent. but with decreasing the size of the finite elements. With the decrease of the size of the finite elements, you have some conversions. You can see that the results converge. Furthermore, some strange behavior before the elastic limit is avoided. Some strange behavior, some regain in rigidity is avoided with more dense mesh. So here, comparison between numerical results obtained for angle alpha 30 degrees and angle alpha 60 degrees. As expected, the load carrying capacity in shear of that adhesive joint for the greater angle is lesser, since, the concrete is better and earlier activated for angle alpha equal to 30 degrees. So one interesting outcome you can have by using damage mechanics, you can see distribution and the evolution of the distribution of damage in the concrete substrate. So we are using here damage mechanics only to model concrete behavior, and therefore we have results for damage only for the concrete substrate. So in Earl Grey you can see damage zones. So these numerical results shows that concrete degradation is not limited in a narrow zone near the adhesive layer, and potentially, theoretically, this may affect the whole concrete structural element, which is reinforced with FRP. So some concluding remarks. A numerical procedure designed to model the debonding failure in an FRP strengthened concrete element has been presented. So we have employed an approach based on damage mechanics or a smeared crack model to model the degradation of concrete in the concrete degradation. It was combined with an empirically based, empirically identified constitutive relationship for shear for the adhesive. It is observed in the simulations that the stress transfer from the FRP plate to the concrete block induces damage in concrete throughout the concrete substrate, and therefore the adhesive joint may affect the overall behavior of FRP strengthened concrete elements. So even though you are using anchorage devices, so this should be checked much more times, but this is a takeaway anyway. So a mesh sensitive study has been presented, and we are working now on exploring the response of the adhesive joint to different loading scenarios. For example, varying the step in the quasi-static loading, also another testing protocols. So the model validity can be expanded by implementing a constitutive relationship for normal stresses. This potentially will make possible to simulate the behavior of high-strength concrete elements reinforced with externally bonded FRP. And we are working to implement this algorithm in the modeling of a large-scale, full-scale structural element, FRP strengthened concrete structural element. So basically, our belief is that numerical experiments can be used with traditional ones to refine the provisions of the codes. So thank you for your question, for your time. If you have any questions.
Yeah, thank you, Todor. So the floor is open for any question, comments. Yeah?
Have you compared your results to experimental tests?
Yes. So given that the variability in the experimental results is, about 15–20%, so we are in the middle here. So this is, to validate the model, and then when the model will be applied in the simulation of a large-scale structural element, we should have another validation, the overall response of the structural element. So here we try to basically validate our model for the interface to be further incorporated in the.
Yeah. Oh, sorry, go ahead.
Yeah, so on a follow-up question, I didn't see your literature review, but the University of Texas at Austin also did models to basically estimate the debonding with finite element and compared it to experimental results and tests. So if you haven't seen those papers, those are by Wei Sun and Nelson Ganu. So they may be useful in some sort as having some.
Of course, the work is underway, so.
Thank you, Mariana.
So I have a question. How did you get the parameters for your cohesive elements?
So basically to match the experimental results. So first we got the parameters for concrete, model parameters. Then we used, how to say, a suggested split of the contribution of each favor mode. So this split allows for assessing, rough assessment of the fracture energy for mode 1 and mode 2. And therefore, we try to have the same area under the curve.
So my question would be follow up, since the failure is in the concrete, how is your model dependent on these parameters of cohesive elements? Or basically, the rule is if it's good enough, so it doesn't separate at the interface, then you're going into the failure into the concrete.
No. So we have three models. One model for concrete, one for the interface, and one for the FRP. So we are putting all together, and we are comparing the global output.
Okay.
So first model by model identification, and then the global output also.
Yeah, hey there.
Did you observe in your numerical simulations stable crack growth and then followed by a dynamic crack growth? Because in my experiments, I observed that the IC debonding happens first of all slowly until you gain enough critical debonding length, and then it goes.
So, how to say, it is more dynamic and it is drawback. So, a reason of the drawback that we have only, how to say, the branch after the elastic limit, let's say the elastic limit is linear, or how to say, almost linear, not constant. In the experimental results, we have seen in the literature that you have some kink. So possibly this can be due to the high heterogeneity of concrete. So even initially the concrete is not homogeneous, you have high variability. So maybe this could be fixed by, how to say, presuming some heterogeneity, so varying the initial elasticity constant element by element. And after the, how to say, the peak, we can have the two phases or.
You don't have to do that if you're capturing the average energy. But the question is, did you get a stable growth and then after gaining a certain length, you go dynamic?
Yes. Yes, but how to say, it's we need a little more work to be more representative.
Yeah, go ahead.
Okay, so I have a question about the material parameters. So can you go back to the FRP model, material model? Yes. So my question is it's a bit challenging to find the usually we test the FRP limited in uni-exit test. So we can easily find the modulus and strength in one direction. But for the other 2-3 directions, how
Yes,
do you find these experiments?
So you can vary the direction of the applied load with the respect of the orientation of the fibers.
But did you consider the modulus in transverse direction?
Yes. All the 5 constants. So yes. So basically, they are here C11, C22. They should be E3, E1 equal to E2, the Poisson's ratio for the 1-2 plane and the Poisson ratio for 1-3 plane, so everything.
Okay. But usually, this was uniaxial.
Unidirectional, yes.
Yes. So, but in transverse direction, like to the fiber transverse direction, you
Yes.
don't consider the strength in that direction.
A long time before I made experiments, so along the fibers, normal to the fibers, and varying 45 degrees with respect to the fiber orientation to obtain the 5 constants.
Thank you.
What did you use for your adhesion layer?
Sorry?
What did you use for your adhesion layer?
So for the time being, it is only this. Maybe it will better to model the adhesive layer with how to say, with
With slip, different gripping, because if you're pulling out the concrete, that means you've got too much adhesion at that point. It doesn't.
So here we are making the assumption that so if you have opening, this is the concrete which fails. And if you have shear, this is the adhesive which fails. So this limits the, how to say, the application of the model for normal strength concrete. So if you need to apply the model for high strength concrete, we need to also to define for the adhesive layer opening. But maybe a good solution would be to model also the adhesive layer, which is, how to say, with.
You have a bond failure.
Yes. So here no, but in the future we are how to say, we will try to make a thin band.
Right. Okay. I got you.
So maybe it will be better, but how to say, we should try.
Sure. Thank you.
Yeah, and there is one question here.
Yeah, thanks for sharing. Yeah, my question is followed by the cohesive behavior. Because for this type of test, the main problem is the contact. For the layer, you're using the zero thickness cohesive element.
No. I do not use cohesive elements.
Yeah.
So I have initially coincident nodes, and I just how to say, govern the position of nodes.
Okay.
So after yes. So I can prescribe
So
the relative displacement of nodes in function of the.
So it's a user-defined element, or
No. Just custom procedure to govern nodes. No,
okay. And also, sorry, yeah.
Yes.
Because you're using the inclined direction to pulling out, it combines the fracture mode 1 and mode 2 pulling with shearing.
Yes.
I mean,
But we are not using fracture mechanics.
yeah, but it's quite hard to pull out that such bulk of concrete out, because I'm doing about a 96 building test with single sharing lab test, and they only attach a few thin layer of concrete substrate on the FRP after debonding. So for this case, it must be easier to pull out the some concrete attached on your FRP,
So,
but not too much.
So here the focus is to try to properly define the constitutive relationships,
Yeah.
to use them further in the, how to say, in a more complex systems.
And can we go back to the last slide? Yeah, the last one, I say here is some failure at concrete, the last one. You just show the result of the test, the simulation.
No, this is damage in concrete.
Oh.
So since we are using damage variable, we can track the values of the damage variable throughout solution. And this gives us image on the damage accumulated in concrete, but within the model. So if it is realistic, is still questions, it should be further. Here, this is a damage in concrete, but it is not failure.
Oh.
So these are finite elements in which some value of the damage variable, for example, 0.3 is reached. And the critical value of the damage variable should be defined. So critical value of the damage variable, this corresponds to failure of the element, and the corresponding finite element do not contribute to the overall stiffness of the system. So just you have a rupture there.
The debonding in the zone is already ruptured?
No, this is damage in concrete. Damage in concrete.
Only
So
concrete, not the adhesive?
So here in white gray you have damaged concrete. So in the zones you have in which you have white gray, for example, the elasticity modulus instead of 28,000 is 20,000. So we have degradation of the material properties.
Okay.
Prior to favor, not favor, prior.
Any further question, comment? Very good conversation here. I love it. Okay, so thank you, Todor.